so we will understand why the integrals of motion for the open Toda chain and for its generalization comes from this, how they can be realized as some particular case of the other constant sign scheme. But now we should remind the home tasks. Do you remember what was the tasks?
One was to prove the lemma you gave us.
Yes, but which lemma?
Well, if you have a solution in the Young-Buster equation, then it must be like it must fulfill the braid relation. Or S equals PR.
Would you like to present your demonstration?
I was also reading about because it's actually very similar to the Ising model.
Yeah.
This relation for the Young-Buster equation, when you have the relation between two neighbors. So I don't know if this formalism is used for solving the Ising model in one dimension.
They're related.
Yeah?
Yeah.
So this is like the right. I will first assume the braid relation with S equals PR. So S23 is P23 R23, P12 R12 and P23 R23. So we can decompose this. So we want to obtain a relation similar to what you have in the Young-Buster equation, something like this. Should be like 2, 3, 1, 3. In this case, it's the opposite. I will use this 1, 2, because I will maintain the last part. 2, 3. Okay. So right now I have R23 here. So I will have to make here to change from 1, 2 to 1, 3 and 2, 3 to 1, 2. And I have these relations that are very useful between R and P. Like this. Well, I can write it like this. 1, 2, 3. So this way I can take 1, 2, 2, 3, and this is 3. 1, 2, 2, 1, 3. Okay. So 1, 2 to 1, 3. We have this. Yeah, okay. We have this. So that's not the problem. And here we have 2, 3, 2, 1, 2. So we can compose this. So it's a new 1, 2, 3, 2, 1, 2. We can do 2, 3, 2, 1, 2, and then 2, 1, 3. And obtain this. This can be proved since okay, we can write 1, 3 like the identity and B. So the first, if I have an element two space 3. I don't remember the notation. It was 3. Like this. If I have this element, and this will be the transpose over YC, this R over XY, and then the same. So this is the same as P to 3, P to 3, and this is R1 to 2. So what we obtain is the conjugation through the transposition. And the same we can obtain it for 2, 3, and 1, 2. This is a bit more tricky, unless it was for me. But we can make this. We can say, well, we make P1, 2 over this element of the basis. Of course, we obtain this. And then over this, and then over this we do R2, 3. R2, 3 with P1, 2 over this element. So by the definition, the first, so this is the second and the third one, so we'll act this. Okay, so it's the same as if you have like Y and R acting on YC. Okay. And then you make again the permutation, P1, and what you obtain is that, I won't make this step, but you will have to change 1, 2, so this element goes here and this one goes here. And then you can see easily that it is equal to, so the first element is the one, so Y goes to the middle and this first element gets affected by R, and also the last. So it's the same as making R1, 3. And we have again the conjugation by P1, 2. So then we can use this. And then, okay, so we have here P1, 2, R1, 2, and R1, 2, P2, 3. This is the same as here. This is the same as P2, 3, R1, 2. So, 3. So, P2, 3. R2, 3, R1, 3. Okay. P2, 3, 3, 1, 2. And now we want to do 2, 3 to 1, 2. But here we have this same as this. This is then B1, 2, R2, 3. P2, 3, P1, 2, R. I did the opposite. So this that way. Okay. So yeah, it's P1, 2, R1, 3. P3, P1, 2, R1, 3. now this 1, 3, you have to send it to 1, 2. Yeah, sorry, I forgot that I was doing this.
Yes, that's okay.
So 1, 3. And now, so this R1, 3 multiplied by P2, 3.
Yep.
P2, 3, R1, 2.
Mm-hmm.
P2, 3, P2, 2, 3, R1, 2. Okay, yeah. 1, 3, 2, 3. So I obtain this, and I have this. I will obtain this. So then I will obvious some steps because it's the same proposition. It's using these same steps, you can obtain again for S1, 2, S2, 3, S1, 2, and then you have the same. You have P1, 2, R1, 2, P2, 3, R2, 3, P1, 2, R1, 2, and again you will maintain R1, 2 because it's the other part of the Young-Buster equation. When you have this last term,
Yep.
this term goes. Okay, this term goes to 1, 3. Okay, this term goes to 1, 3. And this terms goes to 2, 3. And then 2, 3. I have to make the composition again to obtain 1, 3. I have to make the composition 2, 3 to 1, 2, and then 1, 2 to 1, 3. This is made by this composition. 2, 3 to 1, 2, and then 1, 2, 1, 3. Follow the same steps, And 1, 2 to 2, 3, I have over there. And I will take the relation after doing this. It's the same. P1, 2, P2, 3, P2. Okay. R2, 3, R3, R1. So this is the same as this because I can use the symmetric group. This relation, a very well-known relation, the symmetric group. So left-hand side and right-hand side are equal. So this direction is fulfilled. And the converse, we can use very similar.
So it is equal and it is invertible, so we can multiply by this element on the left.
So yeah, of course. So we can do R equal PS.
Mm-hmm.
And we have to, the only thing we have to do is where we have R, use this notation, and then we have to do the same to obtain the break relation. So it's the same.
Very good.
Okay.
Could you say what's your name?
It's right.
Aha. Glad to meet you. If I remember well, the next problem was about the strange solution of the Young-Buster equation with the sine function. Have you managed to find the equation? I give a solution, but what is the equation for this solution? Remember, matrix R, or small r.
So this is what I just tried maybe, right?
Yes, yes. We started to realize this. So I started to demonstrate that this is the good matrix to realize the Poisson bracket. There are matrix Poisson bracket in the Toda case. But the question was does it solve the classical Jan-Baxter equation, which is R12 R13 plus R12 R23 plus R13 R23.
Maybe I can restart. So no. Okay, this is a different one. I tried quantum.
Does it solve the quantum Jan-Baxter equation? I'm not sure. So let us verify. So it's not complicated, but you see in this case we couldn't use this parallel with the symmetric group action because it's something different. It's not the symmetric group. It's not just a transposition. It's some operator that acts in some way. Soon we will see that it is related with the Adler-Kostenheim scheme, but for the moment we don't know, so we have to work it just directly.
Does it fulfill the equation or does it not?
It's a question. Does it solve the classical Jan-Baxter equation? This is the classical Jan-Baxter equation.
Well, maybe an idea could be use the equation and make it act over an element of the base and see if it makes it.
I think it could be done just directly, just using the commutators between matrix elements.
Maybe it's a little bit long to make those calculations. I don't know, maybe you have like a hint that you can use to simplify it.
You see, for example, this term, it could be written just directly. So it's a commutator of sum ijkl.
So I think we should create some cyclic.
Very possible, but it's not difficult. So you see, when we start to calculate it, there is only commutator on the first matrix element, okay, L multiplied by Ej Ji multiplied by ELK. So you see, it's the first term in this. I have written. There are only two terms. Who wants to understand the calculation? We will help you. We will, but it's the best way to understand how to calculate.
Did you just write here sine k minus L?
Yeah. No. Sine, в смысле, in the sense of sine. Yeah. No. Sine.
So there you use Leibniz relation to.
Yes. We have to replace it by EIL delta. I'm sorry, IJ delta JK minus EKJ delta EL. Well, let's do it. Do you want? It's not difficult. But you see, when you push it, it's better to protect. Yes. It's already written, but you are right. It's better to understand all. Yes, it is already. Yes, it is written. But if you don't understand, it's better to write directly. So to write these elements in terms of this definition and to see which terms commute, which not. So you understand what is R12?
R12 is this thing, 1, 2.
Yes, multiplied by 1. Tensorly multiplied by 1.
Yes.
You see?
Yes.
So it's just
Yes.
1. So it is
I
R12.
forgot if on the right or left. So 1, 3 is on the left, right?
1, 3.
Is on the left.
No. 1, 3 means that 1 is in the middle.
In the middle, yes.
Yeah.
Should I write it again? I mean, should I? Yes.
I think it's better to write directly what is R13.
R13 is
So you understand now when you commute this with this one commute with each other and this one else commute with each other. So the only non-trivial term which it is this term. Okay, that's why I have written like this. No, I don't agree. So it's a commutator, not a product. It is already the commutator.
Product will be just only E.
Yeah.
Right?
Yeah, just only the product of EIJ, EKL.
Yes.
But if you consider the commutator, you get the commutator on the first tensor component, in the first tensor component. Do you agree?
Yes. Yes. question about the indices. So here, J and L are dumb index, or which are dumb index in the first line, the first commutator? K and L?
Last?
In the first commutator, R12, R13.
I don't understand. Which indices? Where?
I'm asking, like, are there any dummy indices in the sum?
Yes.
So who are the dummy indices in the sum, in the first commutator?
Here,
Yes.
there is the sum over I, J, K, and L. Over all indices.
All are dummy
Yeah.
indices.
Yeah. Now we have to calculate the I'm sorry. Here, there should be somewhere commutator. Yes, please place the commutator. JI, KL, I suppose. Yes, very good. And here, IJ, KL, J. So here it's a commutator. Okay. Okay. Now we have to calculate all the commutators. They are defined just by the standard formula in DLN, by this formula. And we have to replace all commutators by the exact values. Do you understand the rule? So when you multiply matrix unities, it is non-zero if J is equal to K. In this case, it is equal to EIL.
Yes.
And in inverse order, the product is non-trivial if L is equal to I, delta IL. And in this case, the product is EKJ. So just matrices.
Is this the correct way to calculate for all the bases?
I don't understand what is written.
I mean, if you calculate for all the bases of like in all the.
Well, I don't understand what is written here. What is?
I didn't write it.
Yes. Sign.
He says both all the things are the same.
No. I don't know. I don't think so. No, we need to write exactly. So you see, in this case, the answer is IJKL sine I minus J sine K minus L, and then this IL delta JK KJ delta IL EJI ELK. Okay, then we should simplify the Kronecker deltas here. That means that we have to take here J equal K or K equal J. What is better? K equal J. So there is a sum over three indices with K equal J, sine like this, sine J minus L, J equal K, K equal J. Then E I L E J I E LK, EKJ. It is the first summand. The second summand is the sum, but here we should put L equal I. And it means that it is the sum over IJK with L equal I. Sine I minus J sine K minus I. L equal I. Okay. And minus. It is minus. EKJ EKJ EJL ELK. Okay, so it's the first part of your formula. This is the answer. Please do the same for the second and the third one. Is it principally clear the way to calculate?
Yeah, I think instead of directly writing the commutator, it would be better to write first the operator, the R matrix, and then calculate the commutator explicitly. It would be better, I think.
I was trying to solve this problem yesterday, but I get to a really big thing, so I couldn't finish.
We will try to look
Yeah.
all together. Maybe we find the.
I think we should get one part of the commutator like this, another part is like this, and then it just solving this kind of task. But if we can calculate the other part of the commutator, this and the opposite,
Yes.
and then put them together, it will be 0. Yes. It's not a full source solution.
I'm not sure, but it should be quite close to 0. Should be quite close to 0.
And from
I
this
know.
problem, it should be.
So this is all I minus JK minus L, right? They're the same.
Yes, yes, there should be. Yeah. is one mistake here. So it is until it is I. And please. IJK. Yes, very good. It's the first part, and the second.
Why? I think they should coincide with this one.
No, because the matrix elements are different. No, it doesn't correspond. So you see, they doesn't correspond exactly. There are some terms which vanish because sometimes the sign are good, but it's not the complete coincidence. So you see, for example, then K is greater than I, but J is less than L. These terms cancel each other, but not in general.
Yes. So the answer is 0 or not 0?
Yeah.
Not 0?
No, it's a question. It's a question. I don't know answer. I know the general thing. Okay, we will discuss later what is the general property of this matrix.
So what should I do now?
Yes, we have.
I mean, what should I do now?
I think the third term will be useful to understand if something cancel or not. R1, 3, R2, 3.
R1, 3, R2, this
Uh-huh.
one?
Yes.
Which is this one?
This is what the written thing. What does connect to what part of the equation?
You mean this?
Yes.
This.
Okay. And it is the 1, 3, 2, 3.
It's 1, 3, 2,
Uh-huh.
3.
So we need also 1, 2, 2, 3.
1, 2, 3 is here.
Mm-hmm. Okay. Okay. very good. The homogeneous terms with the same matrix generators. So we have this one. You see they coincide in inverse.
They are yours, yes.
The same one here.
I think
With just the replacement of K to L. Do you agree? Do you agree? And here the similar term is this one. Do you agree?
But with different indices.
It's not important, so we can rename the indices.
Yeah, because all are dummies, so we can write anything we want.
But okay, to make them coincident, what we need we have to change J to L, J to L, K to J, and K to J. Yes, J to L, K to J, J to L, K to J. I. So J to JL is the same, but this is different. So we have to compare the coefficient behind. So we have I, L, E, K, I. I'm sorry, J, I, J, I, E, L, G in this term. And the term here is minus sine I minus L sine J minus L, J minus L. So here we have plus sine I minus J sine J minus L, and we have some signs here, but to make the exact comparison we have to change index J here to L and K to J, I'm sorry, to J, J to L, K to J. Okay? L to J, yes. J to L, K to J. So we have also sine sine I minus L and sine J minus I. You see, all these terms are linear combination of such basic matrices with such coefficients. Could we say that this coefficient is zero or not? Because it's a difference of, it's a sum of different sine functions. Here we have plus. But I have some doubts, but let's verify that this is zero or not.
we could have a try, suppose and see what happens.
Yeah, very good.
So this would be
Minus.
this is plus.
It couldn't be zero because it's odd.
What do you mean?
There are three terms. It could be zero.
Ah, yes. Yeah.
Okay. So the statement is that this R matrix doesn't satisfy the classical Yang-Baxter equation.
It's not zero.
No, it's not zero because we have a monomial with the coefficients which is non-zero. So I know.
This is not correct.
Yes, yes, this is not correct. But could you say that different terms in the sum doesn't compensate this monomial? You see, we have two types of terms. In this term, the indices correspond in the inverse order.
Yes.
So it's in fact it's some product of three matrices in opposite order. It is something like L1, L2, L3, and trace of something like this.
Why we have 3 terms here? We should have 6 of them.
The other terms correspond to different product. You see here the indices are in the right order. Here you have L, and here L, and here I correspond to I. So it's a good cyclic order. And here it is an inverse cyclic order.
There are 2 groups of them.
Yeah,
and 3.
yeah.
But okay, yes.
For example, if we choose such an order, IJK, different to say, but I suppose that they couldn't. J, I, L, J, L. So I suppose that they are different with respect to the cyclic order. So if we can find two monomials which couldn't be compensated. Okay. So the answer is not, but very soon we will understand what is the good equation for this R matrix. Thank you very much. What is your name? Just a minute.
Did we talk about if we take
Janine.
P, substitute by R, does it satisfy? Did we talk about that?
No.
So do you know the answer?
I think it's not zero.
No, in the previous class, Hasib
That
tried.
that is P product.
I think it's not solution. It was the task from the last exercise lesson. Tsui Janin.
Yes.
Nice to meet you. Okay. We practiced in R matrix calculations, what is very good. But now I will give you a definition of the full Toda system. Full symmetric Toda system. It doesn't have such an obvious mechanical interpretation, but it is so it is also very natural and is related with many mathematical structures. So we consider the Lux operator, which is now a symmetric matrix, but with all diagonals. A1n, A12, A1n, An minus 1n, A12, A22, A1n. So L transposed is equal to L.
other positions are all zero.
No, all positions are not non-zero.
But I mean, on other positions of the matrix, they are all zero.
No. All positions are not zero. So the only condition that this matrix is symmetric. You see? So we have, but this this element equal to this one. Okay? So it corresponds to the symmetry condition. And we define the Poisson bracket as the Poisson bracket on B plus. So it is written just by the standard formula IL delta Kj minus delta Li Akj. In all these formulas, I is less or equal to J and K is less or equal to L. So I'd like to say that we consider here the projection of this formula to B plus. B plus, it is the Lie algebra of upper triangular matrices. I is less or equal to J. So you see the elements of the upper triangular part of our Lux operator correspond to generators of the Lie algebra B plus. In the low triangular part, we put just the same generators, and we consider its Poisson bracket like in B plus as the Lie subalgebra of Jelen. Okay. And then we consider the following procedure, which is called the Deift-Lie Nambu-Tamei chopping procedure. We consider such an aggregate lambda E, which is our matrix and then consider it left lower anti-diagonal part, which means that we chopped k upper rows and k right columns. Okay. And then we consider the determinant of this strange matrix.
Why do you need to chop it? Or maybe it's just some interesting properties.
There are some interesting properties that will go slowly. You see, it's not a characteristic polynomial of this submatrix because the diagonal with lambda is not in the center. You see, it is something strange. But if we represent it as a polynomial on lambda, it will be a polynomial, some strange polynomial. It will start with if we chopped k lines and k columns, what is the maximal degree on lambda? Yes, this dimension is n, and we have chopped k rows and k columns. What is the maximal degree on lambda? Hmm?
In minus k.
No.
In minus 2k.
Okay,
Yeah. Lambda n minus 2k. Yes, because each chopping chop two lambdas.
Yeah, this side and this
Yeah.
side.
And what is the principal coefficient at this power?
In front of lambda.
Yeah, in front of the maximal power of lambda. this minor. Okay. So I'd like to write it like delta minus, and which is of order, I don't know, k. Of order k. There are some terms, and what is the lowest term here? and maybe minus 1. What is the lowest term here?
A n minus k.
It is this minor. So I'd like to denote it by minus n minus k. See? So it's the left lower minor of such an order. So it is big and this is small, and there are some additional terms here. So it's some polynomial on lambdas, lambda e k e. And the theorem says that the set, but not all the coefficients, but the ratios for all k, I, and j is an involutive family. With respect to this Poisson bracket. So our task for today will be to study the cases n equal 3 and n equal 4, just to calculate all such functions, to understand which are central, which are Casimirs, which are independent. So let us start to calculate the ratios of coefficients of such strange polynomials, and to understand the Poisson brackets.
So what is actually delta? I mean
Delta, if we have the matrix A, then this is the delta minus of L. Okay. The determinant of this left lower part of this matrix of dimension L.
What do we have to do for n equals 3 and n equals 4?
To write down all these functions and to understand which one are Casimir functions. Yes. Yeah, centers. Yeah.
And if problem is this function.
So in fact, the statement is that the system is integrable. So when we extract all Casimir functions, the number of the rest integrals will be half the dimension. Okay? So firstly, for n equal 3, so we have the 3 by 3 symmetric matrix. So the initial number of variables is 6. Okay? Let us start to understand the case in n equal 3. The first task is to write down expressions for all integrals.
So So ijk is just the delta?
We need to write down this.
I mean, what is I here? Sigma lambda
I n minus 2k is just delta minus k.
Okay.
Okay, but there are other coefficients here. So if you write down all the coefficients, the ratio of coefficients will be integrals. So the first problem is to write all these polynomials, but there are not too much for n equal 3. Okay, I will do the exercise for n equal 3, but n equal 4 will be your n equal 3. In this case, L is A11, A12, A13, A12, A22, A23, A13, A23, A33. Okay? Then I write such a matrix, lambda minus lambda. Okay? The determinant of L minus lambda E 0 without chopping. Just a characteristic polynomial. And it is minus lambda power 3, lambda square trace of L, minus lambda, I will write 1, 2, 1, 2, delta 1, 3, 1, 3, delta 2, 3, 2, 3. You understand this notation. It is the sum of central minors. Okay? And plus the determinant of L, or plus delta 1, 2, 3, 1, 2, 3. The determinant of L minus E1 is the determinant of such a matrix. And it is A12, A23 minus A13, A22 minus lambda. Okay? And it is equal, as we have written, minus 1, 3 lambda, and plus the minor minus 2, but it is the same as, I will write it exactly, 1, 3, and 1, 3, it is minus 1. Okay? It is the minor of the dimension 1, left lower minor, this element. And this minor is the minor of the matrix 2 by 2, lambda, plus A12, A23 minus A13, A22. So the theorem says that trace L, then delta EG, sum over EG, and determinant of L, and the ratio of these functions A12, A23 minus n A13, A22 over A13. It's a commutative family, involutive family. So this is the statement of the theorem. And if I understand well, this function and this function are central. Casimir functions.
Well, Casimir is something, if you act the group element, it will be the same. I mean, not change.
If we calculate the Poisson bracket, it's not a GLN Poisson bracket. It's a different one. It's Borel-Lisa algebra Poisson bracket. But if you start to calculate, these two functions will be central, will be Casimir functions. It means that in the sense of the Liouville integrability, we have to fix the level manifold for two such functions. It will be 4-dimensional, because initially it is 6-dimensional space of symmetric matrices 3 by 3. It is 6-dimensional, okay? After fixing the level manifold for two such functions, it will be 4-dimensional manifold, and there will be two functions in involution on this manifold. So it will be a Liouville integrable system. Let us verify that two such functions are central. So we have to calculate the Poisson bracket of the trace of L with all generators and this one else. Maybe for the trace it is known. In fact, we have discussed this. That the trace function is the Casimir function for the complete GLN.
Yes, so the polynomials and something there was.
Yes, the trace of this matrix. So the sum of these elements is the Casimir function in GLN. So it commutes with all elements of GLN. It means that it will commute with up triangular part. So this is, if you remember well, the beginning of our course, the Casimir properties of this element is obvious. But let us now calculate the Poisson brackets of this function with all the generators. So my statement is that it is the Casimir function.
So on this manifold we have no Hamiltonian so far.
You see, for the moment it is not important. But this function will be the quadratic Hamiltonian, which reduces to the Toda Hamiltonian when we restrict this space to the Toda phase space. So the open Toda chain is some invariant subvariety in this for this system, but it's another question. So the Hamiltonian for us will be one of these functions. So if you want the quadratic Hamiltonian, this is quadratic. But now the question is to demonstrate that this function is the Casimir function in respect to the Poisson bracket on the Borel-Lisa algebra. And your home task 2 will be n equal 4. So
you direct need to calculate the bracket with the base, right?
yes. So you have to calculate the GLN Poisson bracket, but with only the upper triangular generators, because we have only upper triangular generators in our Poisson bracket. They are obviously not Casimir in GLN. So they commute only with upper triangular part of GLN. You see? And algebraically, it is a very important question. So also it describes some Borel subgroup invariants.
My question, can you please explain again a little bit about this
Yeah.
integral of 0th order and 1st order? So this 0 and 1 means like when you chop the outer...
0 means that you chop nothing.
Okay, you just find the determinant of this matrix.
Yeah. And this means that you chop this line and this column.
And find the generate of what is inside.
Just determine it, yes. It depends on lambda. If you do further, it will not depend on lambda.
Just because we come to the lower.
Yeah. So there will not be some ratios of coefficients. There will be one coefficient. So it doesn't produce integrals. So you do it just up to the half the dimension.
And then here we are saying that this thing will be Casimir.
Yeah.
Of JL.
No, of B plus.
So,
Uh-huh. You see, we have only generators with Aij with I less or equal to j.
downstairs.
No, it's, no, it's upper right part of the Lux operator. Okay. And the question is to demonstrate that this function Poisson commute with all such generators. If you realize this function in JLN, in all JLN, it will not be a Casimir function. It doesn't commute with other generators, but it commutes with generators of the Borel subalgebra.
Which is the upper
Yes.
part of
Yeah.
this Lux.
Yeah. Yeah. 0, 1, 0, 2, 0, 3. And this is E1. 1. E1, 0 divided by E1, 1. So this annotation corresponding to this definition. Yeah. There is also E00, which is 1. So in fact, what is written here is also the ratios of
So how do you write this Borel? So what we need to do, we just need to commute this thing with with our the upper part of the Lux matrix.
Yeah.
So,
Not just with A12, for example. Let's calculate the Poisson bracket of this function with A12.
so you take like separately elements
Yeah.
from here
Yeah.
and try to commute with.
Yeah.
Okay. I think we will not be able to do it in time.
Okay, I think we can stop now. So your home task will be both cases to understand better the definition and to make the calculation.